Hey everyone, welcome to the second video for our next unit where we're going to look at another reaction, the addition of water to alkenes. So this is going to be very similar to our reaction where we already looked at the addition of HX to alkenes. And it's going to be similar both in mechanism and a little bit in outcome actually. The outcome is going to change a little bit because we're not adding the same thing, but it's going to be very reminiscent of the reaction we already learned. So the overall and general reaction for this one looks something like this. We have some alkene to start with, and then instead of adding HX to it, we're going to add H2O, but we need to do this in the presence of H2SO4. So when we look at the product for this reaction, I'm going to quickly just duplicate this over. We're again going to be reacting with that alkene similarly to how we did before. And we're going to add a proton across that alkene, much like we did before, to create a carbocation. And you'll see that I'm color coding that hydrogen in purple to show that it's coming from our sulfuric acid. And then we'll make that carbocation intermediate, which we'll talk through the mechanism of in a moment. And then at the end of the reaction, the place where the carbocation was becomes substituted with an OH group. So again, very similar to what we did for the previous reaction, except instead of adding our X, we're now adding an OH. So like I just reiterated, we're reacting with the alkene, but we make an alcohol by adding an OH group, and we don't add a halogen. But other than that, the reaction is very, very similar. The only other little difference here is that this reaction, the conditions here, requires extra acid. And the reason for that is that we're trying to add water. Now, water is an acid. It's not necessarily a very strong acid, and it's definitely not as strong as something like HX. So HX had the acidity that it needed, and then we were just adding that X as our nucleophile in the second step. But for water, water's not strong enough of an acid, and it's also not very good of a nucleophile either. So we need to add a little bit of this extra acid in here so that we can have a nice carbocation formation, and then the nucleophile water will be able to react with it. So let's dive in and start taking a look at that mechanism, shall we? So again, just like we did in the previous video, let's just take our pieces and parts here and start thinking about nucleophile and electrophile. So last time we had the alkene as our nucleophile. We decided that's what it was because the other thing with the proton, the HX, seemed like the better electrophile. So the alkene could absolutely be our nucleophile here, but do we have anything else? We always just want to check that first. Water is definitely something that we put in the category of potential nucleophiles when we defined nucleophile and electrophile, because it has this lone pair of electrons, two of them in fact, which are able to pick up things like protons, right? So which one is our nucleophile? Well, the complicated answer here is that it's both. The water is able to pick up protons as a nucleophile, and it does that in this reaction. Essentially, what's going to happen that we will not need to focus on is going to be these two molecules here together in these brackets are going to be undergoing an acid-base reaction constantly. And that's going to just make some H3O+. Other than that, we don't really need to think about it, so we're going to ignore it, because if you do an acid-base reaction, which I'll draw really quickly here, if we reach out from our nucleophile to the electrophile of sulfuric acid, again, because it likes to give up these protons, right? We can think about it a little bit like being H+. If we did an acid-base reaction that looks like this, that's fine. That's a good acid-base reaction. But the products that we would get over here don't help us move forward in the reaction. So for that reason, we can ignore it. And this is another tip about your reaction mechanism drawing. I'm going to move back up to this previous slide. If you're asked to draw a mechanism, you will always be given the starting material and the product. If you're ever stuck on a mechanism, you have to ask yourself, if I think I want to do this step next, does that help me get to the product? If it doesn't help you get to the product, it's probably not a step that you need to do. So for instance, here we know we need to break the alkene, so you probably want a step where you break the alkene. If you were, say, making another pi bond, like making a triple bond to carbon, you don't need to do that because that's not what's in our product. So focusing on where are you trying to go will help guide you through a mechanism. So Like I said, this acid-base reaction is occurring, but we are going to ignore it for the purposes of this reaction. It's not that important. What we want to do are the steps that are important to getting us toward our product. So let's say that we then are going to determine, yeah, just like we did last time, the alkene is going to be our nucleophile. And this is a pretty safe bet, especially because on the previous slide I said the mechanism is very similar. So that's going to be our nucleophile. Now we have to decide which is our electrophile, water or sulfuric acid. So I spoiled this a little bit earlier by saying that the proton comes from sulfuric acid, but let's see why it can't come from water. If we know that our alkene is the nucleophile, that's good. And let me just copy that over to our box. And then we could reach out and we could use water as our electrophile. Water could lose a proton, but it's not going to. And let me explain why. If we pick up the proton with our alkene, and don't forget your second arrow, drawing it from that bond and scooting those electrons over onto the oxygen, we would get this as a byproduct. Okay, so we would have these two species together in solution. We would make the carbocation, which we know we need for this reaction, but we would also make OH minus. Now, what's the problem with making OH minus in a solution of sulfuric acid? Well, that's kind of like being stood out in the rain, you're outside, it's actively raining, and then you just pull a dry shirt out of your bag and you put it on. You expect that shirt to stay dry for very long? No, you're still standing out there in the rain. It's immediately just going to get drenched, right? So that's what will happen if you try to make OH minus in a solution of sulfuric acid. OH minus is a strong base, right? We may have learned that back in Gen Chem. And a strong base in a solution with a strong acid, you should know sulfuric is a strong acid based on our pKa values, is not going to stay for very long. It's going to immediately just pull a proton off of sulfuric acid and make water again. So that's why we do not want to use water as our electrophile here, because it just doesn't make sense to try to create a strong base in an acidic solution. We'd rather create a weak base that doesn't mind being around strong acids. So all that to say, that is why we want to choose sulfuric acid as our electrophile. Because it's a strong acid, it likes to give up that proton, so this proton itself specifically is going to be our electrophilic atom. So let's go ahead and draw that first step here where we're going to reach out with our nucleophile, come on over here, and then don't forget, once you pick up this proton with your very first arrow, you need to draw a second arrow that breaks that OH bond and set those electrons over on the oxygen. So after that step, we've made some intermediates. Let's see what they are. So again, you're welcome to take this same kind of strategy of sort of just copy and pasting exactly what you had done in the previous step, or what you started with in this case, and then changing what you changed in the reaction. We know we just used that alkene, so let's get rid of it before we forget. And then we picked up one of those protons from sulfuric acid, and we're going to put that on one carbon or the other. In this case, check yourself, does it matter which carbon I put that proton on to make the best possible carbocation? No, it doesn't. They would both be secondary carbocations, so either way, it doesn't really make a difference. So I'm going to choose to put it at that side because that's the side I used in the general reaction scheme. So we didn't do anything with water yet, so that is still here, just minding its own business. And then what's left over of sulfuric acid is this. And we want to make sure that we're remembering to check our formal charges after every step we do. We knew we made a carbocation with a positive charge here, so we have to have a corresponding negative charge to balance it out to make sure the whole reaction side is neutral, just like the side that we started on. Now, we have to think about nucleophile and electrophile again. We can be pretty sure from the reaction that we learned last time that our carbocation is going to be the electrophile because it has that positive charge there. And we said this is going to go mechanistically very similar to that previous reaction. Now, which one is our nucleophile? Go ahead and take a guess now and answer the video question. Which of these two things do you think is the nucleophile? Now, if you weren't sure, that's totally okay. Both of these could be nucleophiles. Let's think about why that is. The water has these lone pair electrons that we were looking at earlier. Those can absolutely be nucleophilic, no problem. What about sulfuric acid? The oxygen on sulfuric acid also has this negative charge, which means that there are several lone pairs of electrons on that oxygen. So if they both could be nucleophiles, how will we choose which one we need to use? Well, there's two things to think about here. One thing that you can think about is which one is a better nucleophile. This is something that we're going to learn more about over the course of this unit, but just for starters, when you consider how strong a nucleophile is, you want to think about if it's stable or not. If something is stable, it's not going to be reactive, and therefore it's going to be pretty weak. And if it's not stable, well, then it's going to be really reactive and a strong nucleophile. So if we're comparing the lone pairs of water and the lone pairs on sulfuric acid's conjugate base, which one is more stable? We could go through the factors like we did in the acid-base unit, but suffice to say for now that if we look at these lone pairs here, they have that pattern that we've been looking at for resonance. There's our lone pairs right there. They're next to a single bond, which is next to a double bond. So these lone pairs are able to resonate around this sulfur-based molecule and therefore gain a lot of stability. Because they're stable, they're not so reactive. Water, on the other hand, has no possibility for those lone pairs to resonate, so it's lacking stability, which means it's more reactive. The other thing to consider, which is the maybe more easy and direct thing that you should consider, is which one do we need to end up in our product, right? If we think back to the last reaction that we did, we had the X halide anion attack the carbocation, and it ended up in our product. So we have to think, do we want most of water to end up in our product, or do we want most of this to end up in our product? If we've forgotten, let's revisit our original slide to see the overall reaction and say, oh, okay, yeah, the piece we want to add is just an OH. And so which of these two is most similar to just an OH? It's water. So therefore, we want water to be our nucleophile. It's the stronger nucleophile, and it's the one that we need to get the correct product. When drawing mechanisms, you always want to be looking for where do you need to go and how can you get there with what you've got. So let's draw in those arrows. We go from nucleophile to electrophile. And since we're not breaking any bonds, we're only forming one new bond. We don't need any second arrow here. We are good to go. Now, for the purposes of organizing this slide, I'm going to move also our sulfuric acid conjugate base over here, but we might want to come back to that later. So let's see what we make at the end of this reaction, shall we? I'm going to move over our former electrophile here. Except now we've gotten rid of that carbocation because it was just attacked by water. And so here's water, just like so. So two questions here. Are we done with this reaction? If you're not sure, go back and double check your product. Here we have an OH group. And if we look at what we've got down here, it's almost an OH group, but there's two hydrogens here. So we can't quite be done yet because, well, that's not the right number of atoms, not the right formula. So the other question is this molecule happy? Am I missing anything? Go ahead and answer the video question now. Is Grace okay to move on to the next step? No, Grace is not ready to move on to the next step yet because she forgot to put a formal charge on that oxygen. It has 3 bonds. That means it's not happy. And again, practice thinking about charge balance. If we took these 2 molecules here, we said, okay, there's the carbocation, which has a positive charge, and water is neutral. If we put them together, they still have to have an overall positive charge. So that's why that oxygen needs to have that positive formal charge on it before we can move on. And it's that formal charge that is the one last thing we need to deal with before we're actually done with this reaction. It's not happy like that. It doesn't really want to be positively charged, and we need to remove one of those protons to get to the correct product. So it has to come off, but where is it going to go to? And so that's where our friend, the conjugate base of sulfuric acid, comes in. If we use that as a conjugate base to pick up a proton, then that does 2 pretty neat things. It, A, is going to allow us to remove that proton and create the product that we know we need to make at the end of this mechanism. So let's draw that in quickly. Here's our molecule. We got rid of that proton, and thus that gets rid of the positive charge on oxygen. But it also does one other cool thing, which is that we've reformed sulfuric acid. So I'm going to recopy this here. And then once we've picked up that blue proton that came from our water molecule originally, we've reformed the sulfuric acid that we started with. This means that we can use a very small amount of sulfuric acid because it just needs to kind of donate a proton for a little bit, and then it will get one back eventually. We call this a catalyst, something that is used in a very small amount that gets regenerated over the course of the reaction. And so with that, we've done it. This is our mechanism for how we add water to an alkene. Let's add a couple of descriptive names to the types of steps that we've done here. So very first thing, our nucleophile alkene reaches out to grab the electrophilic proton. So that is a nucleophilic addition of that proton onto the alkene. And then in the second step, we have this good, strong electrophile, the carbocation, and our new nucleophile, water, attacks that. So this is also a nucleophilic addition, or you might see me call this a nucleophilic attack. Addition and attack are pretty much interchangeable. Let me know if you have any questions about that. So those two steps are very, very similar to what we saw in the addition of HX to alkenes. But then we have this sort of third extra step because we had that extra proton that we didn't want and we needed to get rid of it. So there are a couple of different things that you could call this step, but I'm just going to call this step an acid-base step because that's all we were doing. This proton is relatively acidic and we have a conjugate base here. So that's all we did. It's an acid-base step. But just as a reminder, any acid-base reaction is really a reaction between a nucleophile and an electrophile. It's all interchangeable. So hopefully this doesn't feel too bad based on what we'd already learned in the previous video. But now I want to add something on top of what we learned in that previous video. Again, going back to carbocation stability. So this is the second part that I alluded to in the previous video. And so from that previous video, let's recall that when we have more carbon-based groups around a carbocation, it's going to have more stability. And so we have the trend here that we can write is that our tertiary carbocations are more stable than, our secondary carbocations are more stable than the primary carbocations, which would be more stable than a methyl carbocation. And again, these primary and methyl ones you just will not see. So don't count on them showing up in any answers to anything that we're going to do this semester. We also learned that we always have to form the most stable carbocation. If you have a choice between a secondary and a primary carbocation, you have to pick the most stable one that has more carbon-based groups around it. So that's what we talked about last time. And now let's add another piece onto that. If we have a carbocation and it's in a specific spot, it will do this sort of quick and easy reaction, which we call a rearrangement. And it will do that in order to gain stability. But it has to be, like I said, in a very specific type of spot. So let's look at an example. So here we have a carbocation. We're going to start with some carbocation here, and then we're going to do this rearrangement reaction. But let's think about what exactly it is that we're looking at here as far as the identity of this carbocation and what it's nearby to. So if we look at this carbon, there's a carbon group on one side, a carbon group on the other side, and there's an implied hydrogen there. So it has two carbon groups around it. So that is a secondary carbocation. What is it next to? Well, it's next to that hydrogen. We don't care about that hydrogen. That can't help us. But it's next to a CH3 group here. And it's next to, we don't need to know what the name of this is. But if we look at what's around it, we can get an idea of the identity of that carbon and also this CH3 over here, right? So let's do that quickly. If we draw on our hydrogens, just to remind ourselves that it's a CH3, that is a carbon that only has a bond to one other carbon, and that's our carbocation carbon. So we would classify this carbon here as a primary carbon because it only has one other bond to carbon, the rest are all hydrogen. And then if we look at the other side over here where this hydrogen is drawn in, that has bonds to a carbon here, and a carbon there, and only one hydrogen. So we would classify that as a tertiary carbon. So what we'll see over the course of this carbocation rearrangement is that we're going to move that labeled pink hydrogen from that tertiary spot to this secondary spot. So you can sort of see just the movement of that H. That's all that's changed over the course of this reaction arrow. But what has that done for us? Why does that help? Well, if we look at now where our carbocation is sitting, it's sitting on that carbon that we already decided was tertiary. So this is now a tertiary carbocation, which is more stable, right? So if we think about where we started out with secondary, and then we were able to go all the way up to tertiary. That's an improvement in stability. So that's why this is sort of a quick and easy thing to do, is because we allow ourselves to gain more stability over the course of this little rearrangement reaction. Now let's draw some reaction arrows to show how this transformation has to take place. It's a little bit odd, but what we're going to do is just kind of pick up that hydrogen with its electrons and move it. So to be super clear about that, I'm going to fill in this bond here with 2 electrons. So when I say take that hydrogen with its electrons, that is what's going to happen, but I've sort of said that backwards, right? The 2 electrons in this bond are what are going to move over to that positive charge, and the hydrogen just kind of comes with it. So that's all we're going to do, is just draw a single arrow that shows the movement of those 2 electrons and therefore the hydrogen that goes with over to that carbocation. And then we get this carbocation as a result. So this is a carbocation rearrangement. You may also hear me call this hydride shift, because when we have a hydrogen that has a pair of electrons, we call that hydride. So this hydride shift or carbocation rearrangement is something that you will see, but only in certain situations. Only if you have a carbocation that is adjacent to a tertiary carbon like we had here, will you see this rearrangement take place. Secondary carbocations could rearrange, but it's just not going to help them at all. So we want to make sure that we're only rearranging to make more stable carbocations. That's the only time that it's going to happen. So let's take a look at that mechanism. And we're actually going to walk through an extended version of this reaction as though this was maybe a predict the products question that you wanted to just step through to figure out what the product was, or in case you were asked to draw a mechanism. So we're going to start from this position here, see how we can get from that step 1 to step 2. And let's say this is under the conditions that we're learning about today for the first time, where we're going to be adding water to this alkene. So first things first, we need to get rid of that alkene. And so we just practiced this earlier. We're going to use our H2SO4 to provide a proton to our alkene that is the nucleophile. So again, feel free to label these with nucleophile, electrophile if you like. I'm going to skip a little bit on that for time's sake. So we're going to reach out from our alkene nucleophile, pick up that hydrogen, and don't forget to break that second bond there between the oxygen and the hydrogen. And then we will have delivered that proton to one side or the other. In fact, let's make this a specially labeled hydrogen. Let's label it in orange. And so I will also put some carbon labels on here. I'll call this 1 and 2. In order to make the carbocation that we just made, answer the video question now. Which carbon do we put that orange hydrogen onto? Hopefully you can tell that we needed to put the orange hydrogen here on the end of this sort of chain, because there were already 2 hydrogens there. And that allowed us to set the positive charge at 2, which also happens to be a secondary carbocation that would be more stable than if we put it out here on the end, which is primary. All right, so we've done that. That's the first step from our traditional mechanism. And now this second part here, this is the actual hydride shift part or rearrangement part. Let's practice drawing how that occurs. Again, just a pair of electrons with that hydrogen coming along for the ride. We'll scoot those over with a single arrow to sort of fill these electrons. The way that I like to think about it is taking these electrons in that bond and filling them into that hole that is a carbocation. And then once we've done that, we've rearranged from our secondary carbocation to our tertiary carbocation. And we're very nearly done. Well, let's finish this up. If we take this tertiary carbocation, now what do we need to do in order to continue on this mechanism and make a product that has an OH in it? We need to bring in our nucleophile to attack at that good electrophile carbocation. And so in the case of this reaction, that is going to be water. So we can draw water coming in as our nucleophile, attacking that carbocation, like so. And then we will have made a new bond from that carbon to the OH from water. But we're still not done because we have that extra proton there that we do need to get rid of. So we will be doing that with our conjugate base of sulfuric acid that we made, but we didn't draw it out earlier. Here it is. And then we'll use that to pull off this proton here. And don't forget to break that second bond to restore the charge on oxygen. And that will allow us to get to our final product. We'll just copy this over quickly. Get rid of that hydrogen, get rid of that charge. We'll end up with our product that looks like this. So this is something that you need to be suspicious of anytime you're asked to draw a mechanism that seems like it doesn't quite make sense. If we think about what we've already learned about alkenes and additions to alkenes, here's our alkene. This is shown up between carbons 1 and 2, but our product has this alcohol here on carbon 3. If we continue our numbering the same way that is, let me draw that out explicitly. This is carbon number 3. So how is that possible when the alkene was at carbons 1 and 2? It happens because of this rearrangement. So if you're asked to draw a mechanism and it seems like the product doesn't really make sense because it's not where the alkene was, there's probably a rearrangement going on. If you're looking at a predict the products question, that can be a little bit tougher because you won't see what the product is that you're trying to make. You're trying to predict that. So you'll have to stop and say, okay, I see where my alkene is. Is that close by to any tertiary centers that I might want to rearrange at? Since rearranging is for the purposes of stability, we basically have to do it. So if you can perform a rearrangement like this to make a more stable carbocation, you absolutely must do it. There is no other way around it. There's one other thing that we may see for rearrangements occasionally, and that's something that looks like this. So similar to what I just mentioned, if we look at where this alkene is, again, I'm going to give it some numbers. We found that the alkene between carbons 1 and 2 again, but our alcohol in the product ends up at carbon 3. So you might say, okay, yeah, well, rearrangement happened, but this doesn't look the same as the rearrangement that we saw before. Because if we think about the carbons that are involved here, we would probably want to make a carbocation at this position because this is secondary. Our end carbon here is primary. And again, these have nothing to, these numbers matching up has absolutely nothing to do with one another. It's just a pure coincidence. If we look at carbon 3, that's also a secondary carbon. And I just said that secondary carbocations wouldn't rearrange with other secondary carbocations because it's not that big of a change in stability. But there's something very special about this molecule. So let's start drawing through the mechanism, and I'll point out exactly what happens and why. Same as before, we're going to use sulfuric acid as our proton source and our electrophile. We will pick up that proton using our alkene as the nucleophile. And let's go ahead and duplicate this, erase some of our annotations here. We used our alkene, and so now we have a positive charge here to make that secondary carbocation, and we just added the proton out here at the end. Okay, and now it seems as though a rearrangement must happen here. So I'm going to label these rearranging protons again in pink. Only one of them is going to move. We can pick either one, it doesn't matter. So we're going to take it and its pair of electrons and scoot it over there to rearrange to this other carbocation. So now one of those pink hydrogens has rearranged to that carbon 2 position, and the other one stays there at carbon 3. And the positive charge is now on carbon 3. So this all may seem familiar from the arrow drawing that we've been doing so far, but why? Why did I do it? Well, the answer has to do with our friend from Unit 1, resonance. And if we look at this ring is kind of a special thing in organic chemistry. Organic chemists really love this ring. We call this ring benzene. which you may have heard of before, or maybe not. But benzene, having those double bonds at every other position in this six-membered ring, makes it really special, and we'll actually learn more about that toward the end of the semester. But until then, suffice it to say that there's a lot of resonance available to us here, and that's good. That's a stabilizing factor. So what you should take away from this is if you can move a carbocation to go kind of just one position over and put it next to a benzene ring, you absolutely should, because that is going to be nice and stable. And let's put a little note down here that we're gaining some stability from resonance. And now that we have that carbocation in the place that makes sense based on what we know we need to make for our product, we can finish up this mechanism. We can bring water in as our nucleophile that will attack our carbocation. Duplicate this one more time. Erase our annotations because there's entirely too many of them. And last thing, do a little acid base step with our conjugate base of sulfuric acid, like so, and we'll get to the expected product. So there's a little tidbit about the mechanism by which this happens. So hopefully you're starting to see why this might happen, but we also have a couple of rules that are important to mention so that we can do these rearrangements in only the best and most logical ways. So the very first rule is if you can rearrange, you must. There's a couple of caveats to that. We want to rearrange, but we only want to rearrange to whatever is directly next to us. We can't do this over the other side of the molecule. It has to be immediately next door. That's why when we had the carbocation here in the middle of the molecule, we looked at this carbon and this carbon. We ignored these methyl groups out here because they're too far away. Only the immediately adjacent neighbor carbons are available for us to rearrange to. Whatever that neighboring carbon is must have an available H that will be the H that does the hydride shift or the rearrangement. As you can see, the one that we've got here labeled in pink is important because that's the one that actually ends up moving. So if you do not have an adjacent hydrogen, you won't be able to do a rearrangement. And lastly, you could rearrange all day if you wanted to, but I'm not going to ask you to do that. I'm going to ask you to only look for one rearrangement per any given mechanism. That means that you could rearrange once, but you shouldn't rearrange any more times than that. If there's a tertiary carbon, but it's too far away from the position that our alkenes started out in, it's just unlikely that we're going to rearrange that many times to make it to that product. You'll be expected to only rearrange maybe one time per mechanism, and every mechanism is not necessarily going to have a rearrangement in it. So with those rules in mind, let's take a look at a little bit of practice. So here's some predict the product questions, and let's predict to see if we can figure out the outcome of these reactions. So let's take a look at this first one. We know that over the course of this mechanism, we're going to react with our alkene, create a carbocation, and then we're going to add water to it. And by that, I mean we'll end up with an OH at the end. Since these are predict the product type questions, you do not need to draw the mechanism. I would recommend, however, drawing a quick sketch of what your carbocation is expected to look like. That way you can check for rearrangements. So I'm going to copy this down here. Sometimes you'll see me draw underneath like this to show that we're going to go through some intermediate and then we'll go to the product. Now this is not a mechanism, it's just a little quick shorthand of something to help you work through the problem. So we have carbons here. Let's give them some numbers, 1 and 2 again. Let's see, which carbon do we want to hold our positive charge? Which carbon do we want to be the carbocation? 1 or 2? Hopefully carbon 1 is screaming out and saying, I'm a primary carbon, you cannot put a carbocation on me, it has to go on carbon 2. And then let's think about this carbocation and see if there's any point in rearranging. So if we look at what's immediately next to it, we have this position here and this position here. So this one, as we already mentioned, is a primary carbon, so it would make a primary carbocation. That's bad. We don't want to do that. Over here, we have a secondary carbocation, and that's okay, but that's not really any better than our existing secondary carbocation. So we're probably not going to want to rearrange. Now, if you're thinking, oh, but Grace, what about this over here? This carbon is tertiary, and you're right, it is tertiary. But this goes to the last point I was making on the previous slide. It's too far away, right? We would have to rearrange to, let me put some carbon numbers on here first. And I'll erase these notations just so it doesn't get too crowded. We're starting on carbon number 2. We would have to rearrange to carbon number 3, and then to carbon number 4, and then over here to carbon number 5. That's too many rearrangements, so I wouldn't ask you to do that. It's just not going to happen. It's unlikely. It's more likely that this highly reactive carbocation will just run into a water molecule and make the product right here at this carbon number 2. So in this case, there's no rearrangement taking place, and we can instead predict that the product will look like this, where we've added the water and created an OH group at carbon number 2. All right, how did that one go? Feel free to take a moment to pause the video and predict for yourself the product for this next question. All right, hopefully you've got a good guess. Let's take a look at this, analyze what our carbocation might be, and see if we need to do a rearrangement. So first things first, let's put some numbers on here. I'm going to just number this around the ring here. You don't need all 6 of these necessarily, but just for completeness sake, we'll put them in. We're going to react with that alkene first and put the carbocation at one of those 2 carbons, either 2 or 3. Answer the video question, which carbon do we want to place the carbocation at? Carbon 2 or carbon 3? Carbon 2 has 1, 2, 3 other carbons around it, so carbon 2 is a tertiary carbon, and that means that's the best place that we can put a carbocation to begin with. So we're going to put it there. Now, is there any point in rearranging? Nope. All the rest of these carbons have only 2 other bonds to carbon. They're all secondary carbons, except for carbon number 2, and of course this methyl group out here, which we're not worried about because we know that's a primary carbon and we don't want to go there. So we're actually just going to leave that carbocation as is and do no rearranging whatsoever. That means that we will go directly to the product, and that will look something like this. Where now we've added the OH there at that carbon that has the most other carbons around it, the tertiary carbon. How's that one feel? Hopefully you got it. What about this last one? Go ahead, take a moment for yourself, predict the product for this reaction. Okay, let's see what we get. Again, I'm going to make a smaller copy of this molecule down here. Oops. Really small. And let's put some numbers in here. So we have 7 total carbons, and the alkene is between carbons 1 and 2. But that's not going to stay there for long because we need to make 1 carbocation either at carbon 1 or 2. So answer the video question, where do we want to make our carbocation? At carbon 1 or 2? So hopefully the pattern is becoming clear here. We always want to go for the carbon that has more other carbons around it, and that happens to be carbon number 2 in this case. And now we need to check for rearrangements. Are there any carbons nearby that seem like they would be good to rearrange to? Answer the video question now to tell me if you think there's a rearrangement we need to do. When looking at this, I definitely am seeing that carbon number 3 has 1, 2, 3 other carbon groups around it, and therefore happens to be tertiary. So there's 1 hydrogen there that we could rearrange in order to make a tertiary carbocation. So let's draw that quickly. If we rearrange this, move that pink carbon over to carbon number 2, we'll get something that looks like this. Where now that positive charge is meant to be sitting right here on this carbon, the tertiary carbon, and so that makes a tertiary carbocation is much more stable than the carbocation we started with. And with that, now we can do the next step of the reaction and predict the actual product will look something like this, where we instead react with our nucleophile at that tertiary carbon and not where the original alkene was placed. Okay, how did that one go? Hopefully these ones are getting a little bit easier to start to predict. And so with that, we got some things that we need to practice. The reaction mechanism for adding water to alkenes, like I said, is very similar to the previous mechanism that we learned, but you have to remember that acid-base step at the end. Little things like acid-base steps, forgetting your second arrow, and formal charges are good places to lose points, so make sure that you're practicing them well. We also want to practice the mechanism of rearranging those carbocations and also identifying them, recognizing when and where you need to rearrange to. If this feels comfortable, go ahead and start looking ahead to the stereochemistry of addition reactions. There will be a short video on that coming out shortly. And then after that, you can start to think about what alkenes are doing in your water bottle. More on that to come. Until then, if you have any questions, go ahead and please leave a comment here, post in the discussion forum, send me an email, or come to office hours. Take care.